Okay. So this is always that beginning part where I have to check if the stream is working. But it seems to be doing something, so let's double check. Okay, sweet. Okay, that looks pretty good. Let's put that in a browser where I can actually see what people are typing. It's working. Great, and I can also see that people are joining, and we can do chat. Hello. Oh, and I'm in chat. I'm using my personal account, but that's, I suppose, fine. Great. So, hi everyone. What I wanted to do today is just maybe a little bit different, because I figured maybe an interesting way to think about algorithms is to maybe also just talk about some properties of algorithms that allow you to do things completely differently. And just to give an example, like I could maybe give you the task of classification, and then you can say, well, oh, there's classification algorithm A and classification algorithm B, and all that's great. And I can also talk to you about outlier detection systems that can maybe detect an outlier. Again, we have algorithms for that. All that stuff is great. But sometimes it's also nice to sort of wonder, well, is there maybe something general for many of these problems? Maybe in such a way that I can maybe use like one I will call mother algorithm that can actually do all of those things. And what I'm about to suggest is a little bit more in the realm of creative freedom and rethinking things. I'm about to do stuff with Gaussian mixture models, and I'm not going to suggest that this is like the best way to model stuff. But I have found these Gaussian mixture models just to give you a little bit of intellectual freedom. And I'm also kind of want to highlight just how much flexibility you can get out of them, because it's kind of crazy if you think about it. But before going there, I do think it will be good maybe to first just kind of explain and highlight how these things kind of work. What's the nice way of doing it? Yeah, actually, let's not do the full whiteboard, but what I will do is just go to this screen over here and just maybe add a bunch of white space. So I'm going to make this a markdown thing, and then a trick that you can do actually, by the way, like you can add these break statements. This is just normal HTML, but if you put that in markdown, you basically cause a new line to appear, and then you get a nice blank screen, which is great if you're doing explainers. And just to confirm, let's select a dark color. This will go ahead and work. Okay, so I'm about to like do stuff with Gaussian mixture models, but it might help maybe at first to explain how these things kind of work and what they do. So you might be able to imagine that we've got some sort of a data set, and it's one column in the pandas data frame, and they're all just kind of numbers. So okay, fair enough, that's cool. And from there, what you could do is you could make these histograms. So you can imagine that you've got this bar chart that would sort of explain to you what the distribution of the data that you've got is. So that's something you could kind of go ahead and calculate, and then you can get kind of a histogram chart like this. So that's a histogram. But then you say, maybe we want to model that as if it's a probability distribution. And then what you kind of want to do is maybe fit a curve, like the normal distribution, let's say, that kind of looks like this. And I'm going to go for a slightly more contrasty color. So I think red might be better. So we're going to see if we can fit like a normal distribution. And if your data kind of looks like this, that's a pretty easy task, because the way you do that is you just calculate the mean from the histogram, so to say. And what you can also do is you can calculate the variance. And the mean and the variance are the only two things you need to sort of summarize this particular data set, because it kind of looks like a normal distribution, and life is easy. But let's now consider a situation where life is maybe not that easy. Let's again make sure I've got the right color. But let's again consider a histogram. So I'm going to draw some thick bars over here, and yeah, let's pretend that that's kind of a normal distribution, and then there's a little bit of data there. And let's say that there's like another distribution here, but it's really sort of thin and spiky, let's say, but also a histogram. My drawing is not necessarily that great. But if you were to apply like the same method of thinking or the same trick over here, you will notice that it doesn't work. Mainly because if you were to calculate the mean, you would end up somewhere over here. And if you were to calculate the variance, it would kind of get huge, right? So the maybe normal distribution that you would fit would kind of look like this. Maybe draw that a little bit more centered. But it would basically just, it's hard to draw, but it's kind of like this smooth thing on top. And you can tell yourself, well, this is a normal distribution, and it sort of summarizes this data set. But you can also just see the mismatch with what we're actually dealing with. What you kind of want to do instead is say, you know what, maybe it's fine to have two normal distributions in this particular case. And what I'm going to do is I'm going to figure out the two best places for two normal distributions to sit. And then if this normal distribution captures like, I don't know, 60% of the data, then I'm going to give that distribution 60% of the weight. And if this distribution fits about 40%, we're going to give that 40% of the weight. But we're going to mix a bunch of these Gaussians, and that's like a better way to get an estimate of a probability distribution over your data set. That's kind of the thinking here. And this is basically what Gaussian mixture models do. There are a lot of interesting and cool things in terms of implementation that they do as well. Like if you have an algorithm book, it's a fun read. How they are trained is not entirely unlike k-means. So a lot of it does feel like you're looking for a good centroid that kind of represents a cluster of the data. It's just in this case, it's not necessarily a hard cluster. It's kind of more of a soft cluster where we're also trying to fit a normal distribution. I do want to maybe take the moment to shortcut. There we go. To just look for a GIF. So if you look for Gaussian Mixture Model GIF, you usually end up with good-looking GIFs. Yeah, let's go for that one. Oh, you have to pay. That's kind of a shame. I'll just zoom in instead then. But you can kind of see here, at least, you see some data with some distributions. You can kind of see the ellipse that represents the... can I download that? Actually, it would be nice to have that on a full screen. Maybe different GIF. Yeah, it's... oh, actually, this one is, I think, on... maybe on Wikipedia, but anyway. The thinking here is that we're going to basically have an algorithm that's going to fit all these Gaussians on our behalf, and that's going to be quite useful. And again, the main thing we're trying to do here is we're just trying to get data going in, and then some sort of probability distribution that comes out. That's kind of the plan. That's kind of what we're going to be going for. I made a very, very short little demo to sort of play with, and the goal for now is just to sort of appreciate what's sort of happening under the hood. And once we kind of appreciate that, then we can start talking about some sort of kind of weird and out there, but definitely not necessarily meaningless applications of the Gaussian mixture trick. But I hope the task is clear. Like, the reason why we have Gaussian mixtures is because we want to estimate probability densities. There are also other algorithms that do this, by the way. It's just that Gaussian mixtures have a couple of interesting properties. So, okay, how do we explore how they work? Well, I figured I might draw a data set. So here's the data set that I drew. There are two colors here. We'll get back to that. But for now, at least, I hope we appreciate this is a shape, and we would maybe be interested in having some sort of a probability density over this. And it would be especially nice if we could maybe recognize that if I see a new data point appear over here, that would kind of maybe not fit the distribution of this data blob that I've generated sort of all the way over here. Like, that's the thing I'm kind of going for. Black color, good. So, okay, draw data. We've seen this widget before in this stream. So this is a thing I drew. And then I can also just grab the thing I drew just from the notebook. I have this kind of fancy thing over here where I drew it. I'm able to scatter it. So I'm also going to use this data set for my Gaussian mixture stuff, so to say. So, can we do Gaussian mixture stuff? Yeah, we can. And let's keep it simple for now with the defaults. So the way that this is currently set up is I'm from the mixture submodule, I'm grabbing a Gaussian mixture object. This is a thing that has a fit method. So what I'm able to do is I'm able to say, hey, Gaussian mixture, fit on the data. But this Gaussian mixture is a bit different than other systems that you might have inside a scikit-learn, because let's use the proper mouse for that. And oh, mute keyboard, always making things complex. But if we have a look at the docs of the Gaussian mixture, right, we can sort of see that all of these parameters kind of just go in. But if we have a look at the methods that it has available, like what I can do is I can say fit it. But then when I predict, what I'm effectively going to be predicting, if I recall correctly, is which Gaussian that I've generated the data point belongs to. So the predicting that we're doing here has nothing to do with an actual label. That's sort of an important sort of distinction to make here. Usually in scikit-learn, whenever you see predict, that really means that we are predicting towards something. But because the Gaussian mixture is really just learning a distribution, it's kind of like a special citizen in that sense. So the predict method should not be interpreted as such. And that might actually be good to just demo, actually. So if I take that model, so let's go in. If I take that model that only has like one component, and if I were to say, well, let's see if we can make a prediction, and let's have our data set X just kind of go in. Yeah, then all the predictions say, I've only fitted one component. There's only one Gaussian here that I've added to this whole system, and every data point just belongs to that. So that's a method we're not going to use. It's not that useful for something I'm interested in. The method that is actually super useful, and this is a method that you don't see on many scikit-learn objects, is this little thing called score samples. Oh wait, my mouse cursor was up. I should be able to draw, yeah. Random hardware failures, that's always just annoying. Maybe if I unplug this Wacom tablet and plug it back in again. Okay, so I am able. What is this? Okay, can I turn off the flashlight? Thank you. Okay, the drawing app is broken. That's a bummer. We'll figure that out. But I'll just use the normal mouse then. What is this? Hang on. I think if I do this. Sorry, folks, but I do want my software to just kind of work. This is incredibly annoying. Is there like a button that I've pressed accidentally? Okay, sorry, folks. Okay, now we're sort of back. I accidentally seem to have lost control of my app there for a bit. Still not able to properly draw, though. Okay, so we'll worry about that later. Anyway, sorry about that. We'll just use the normal mouse. So, score samples. I'm able to score samples here. And what that basically does is... actually, can I just use... It would be nice if I could draw something. Can I not even draw a line? This is the last time I'm going to try this, folks, but like I do not understand why on earth it would not allow me to draw. Bummer. Okay. Anyway, the way to interpret these score samples is you can imagine that if we've got this normal distribution, right, like that shape that I was talking to you about, then we can also associate each and every point with a likelihood value. And that's what that score samples does. I believe this gives you the log likelihood of each and every point. And maybe the best way to explain that, I'm going to cancel out some of the code over here, and we're going to come back to that in a bit. So let's do this. Oh, there we go, and I should be able to run this now. Yep. So let's set the color. Actually, we do want that. So what you're looking at here is just a little bit of code where I'm creating a new data set that's going to be random, but is going to span the entire space of the data set that I drew. So it's going to have an x-axis and y-axis, and those are going to be basically the x values over here and the y values over here. The reason I'm doing that is because then I kind of have like a distribution of all sorts of points on the background that I can draw stuff over. And here's what that would sort of look like. So you can see the blue points. Those are the points that I actually drew myself. And then you can kind of see the likelihood distribution, as it were, of what the Gaussian mixture is doing. So you can see that in this case, I've got only one component. And the Gaussian mixture model at this point is sort of saying, well, if I have to figure out a way to summarize this data in 2 dimensions, kind of the only thing I can do is just make this big blob, and it's going to be somewhere in the middle of this data set. And that's exactly what it does. But to get a bit more of an intuition going, what would happen if we have maybe 2 Gaussian distributions? That will be slightly different. So let's run that. And when you do this, you do get the impression that there are actually these 2 hills that have sort of been estimated in this space. We've got one hill kind of more on the left-hand side, and another hill kind of more on the right-hand side. So that's pretty cool. Let's add like a few more. Let's maybe not do 2, but let's maybe add like 5 or something, right? See what happens then. And then you can actually see that the shapes get kind of more pronounced. And we also see that there's like a little bit of green in this sort of circle in the middle over here. And you can see that this like sort of line, there seems to be kind of a line shape around here. There's kind of a very thin Gaussian distribution that's being spun up there. And you can kind of see the effect in the corner over here. You can kind of see that there's like a straight line that's very thin that's being fitted there. Let's now kind of do the somewhat more extreme thing. I'm going to do 25. So I'm going to do lots and lots of small distributions now. And, you know, we haven't really captured the distribution just yet, right? We're not there. But you do kind of see that the more Gaussians that I add, it can overfit a bit more on this data set. And it might be what you want. And we're going to do like the one final thing where we kind of go overboard. Let's do 100 Gaussians. And yeah, here you can just see that we are definitely sort of overfitting, and this shape is, you know, there's lots of these thin little jaggedy edges, so this definitely feels like we're doing too many. So I'm going to go back to 25, and we're going to keep that for what it is. And, you know, this is not necessarily going to be perfect. Actually, let's go for like a few more. Let's go for, I don't know, 45. I don't know, some other number that's not quite 100. Yeah, okay, let's go with this for now. But anyway, like, one thing that I do hope that you appreciate, if I were now to maybe not draw, so yeah, I'm not going to draw the original points. And maybe what I should do is, yeah, actually, I think this is kind of fine. But what you can actually kind of see here is that sort of the distribution that I could be sampling from theoretically. It's an approximation. It's not necessarily perfect. But you do see that we at least fit some sort of a distribution. Maybe the data was generated from something like this. Like, that's something you could wonder. And there's actually something you can do that's kind of cute with that. So one thing you could do, we could call plot scatter one more time. But in this case, this is also kind of rare for a machine learning model to do, but you can ask the Gaussian mixture to sample new data. So just as a fun thing, let me double check the docs there, like sample. Yeah, I just have to give it the number of samples to pick from. So I'm just going to go with like 1,000 data points, let's say. And let's call that S because we are sampling, and S, we want to select the first column, and then we have S, and we want to select the second column. Just thinking out loud. Did I not do that the right way? Let's just check on S. Oh, right. So it's going to give me the coordinates, and then it's going to give me the cluster that it belongs to. And I am, in this case, only interested in the coordinates. So I can do the, I'm going to save the stuff that I'm not interested in into a underscore, and then this should go ahead and work. And okay, like this is the data set that, let's move that one down. All right, and let's undo that comment, and let's just see if we can compare. Like the blue dots are the stuff that I've been sampling. That's actually kind of not the actual data. The orange dots are the things that I've actually drawn. But this is actually not bad. Like we seem to have some sort of trick that can generate data that looks like the thing I drew originally. And of course, right, like the data that I've got here is illustrative. It's something I drew. It doesn't necessarily represent something that you'll notice in reality. But still, I hope at this point you do kind of go, hey, this thing does a few things that just normal scikit-learn stuff doesn't. And that's actually just kind of interesting. But let's not get confused by cool fancy tricks. Let's now actually start thinking like, hey, is there something here that's useful? Because that's actually maybe more interesting. And I would argue there's actually plenty that's useful here. So I'm going to comment out the last experiment that we just did. If I were to run this, yeah, and let's go in there and let's turn on the distribution chart that we made. So, sort of like that. All right. So, okay, can we now do something useful with these Gaussian distribution thingies, right? And now let me think about outlier detection a bit. So you would kind of hope, right? Like if I were to maybe do a point that's like around here, let's use the brush. So if I have a point that's kind of around here, right? I would argue that's kind of an outlier. And at the same time, it looks like the region I've got over here is like green. So the score that the Gaussian mixture is assigning to that region should also be low. Oh. So maybe if we're able to fit a Gaussian mixture properly, like for some definition of proper, then maybe what we can also do is we can say, let's use that likelihood score as a proxy for being an outlier or not. So what I could do is I could say, well, let's take the 50% quantile of all of those scores that we saw in our training data, and let's sort of now color this whole data set by saying, well, the likelihood needs to be above the 50% quantile, and otherwise give it a different color. And then we kind of get something like this. So the yellow points indicate if you're kind of like within the quantile region that we find agreeable. And then the dark colors indicate that you're outside of it. And one thing I could do is I could maybe sample just a little bit more points, just to sort of make that picture a little bit more clear. Don't want to sample too much because that'll slow stuff down, but I do think this is slightly nicer. But yeah, you can sort of see like, okay, we sort of have a tuning knob here to do outlier detection. The thinking here is that if you have a probability distribution, then you also have a method of saying, oh, this region is more likely than that one. So you could maybe build a outlier detection system right on top of this. And another thing that's also just kind of interesting is you also have a pretty reliable tuning knob. Like you could say, well, maybe I don't care about the 50% quantile. Maybe I want to be just a little bit more strict. Maybe the 70% one. Right? And in this case, you can also see that some of the training data points actually are going to be detected as outliers here because our definition of likelihood is just a little bit too strict. But it's still kind of nice. Like we have a pretty, I would argue, interpretable tuning knob for our outlier detection system. There are lots of assumptions in this chain of thought, right? Like you have to have data that fits a Gaussian mixture model. Maybe you're dealing with categories, right? Like that's not going to fit the Gaussian mixture model super well. You're also going to assume that you find the number of components that fits this data kind of well. There's also some interesting numerical details in the Gaussian mixture model. If you don't set the random seed, you are at risk of something that's non-deterministic. So technically, the Gaussian mixture algorithm will always converge, but it will converge in different areas, right? So that's also something that could theoretically go wrong. But in terms of, hey, this mother algorithm seems to do something that is pretty cool, that is something we definitely do have. So we have an algorithm that can give us likelihood scores, it can sample new data for us, and it can be used for outlier detection. And not a lot of systems are able to do that. So a very good question just came in. Like, is there a way to automatically select the number of components? So there are two that I'm aware of. One of them is that you just come up with a metric that you like, and then you just do a hyperparameter search, and you use that metric to make the decision for you. The hard part here is coming up with a metric that you might like. Like, that's going to be for sure the hard part. That said, that might actually be fun to show. Actually, yeah, so the video is still looking good. So if you were to go to the scikit-learn docs, scikit-learn Gaussian Mixture Model, there you go. And that's the one I was looking for. There is a, in the mixture module of scikit-learn, you'll have a Gaussian mixture and a Bayesian Gaussian mixture, which is a bit more fancy. So it's a lot of math that's happening internally, but basically there are you're going to make a few assumptions about the distribution. I believe there's an assumption of like a Dirichlet process in the background. This is math stuff. Like, don't worry too much about it if you're not knee deep in probability theory. But basically, the way I would describe this is it is a mathematically principled way to go about choosing the number of components. The one thing that is a downside here is that this is computationally more expensive, but you're going to use some arguments from probability theory with a few assumptions to make this decision for you. It is principled. There is some rigor involved with this. It's just that personally, I do think if you're able to eyeball it, that's also just usually fine. And the grid search with a metric tends to be less computationally intensive. The big downside of the Bayesian variant is simply the fact that it is more compute intensive. But you can play around with it. Like, definitely give it a look. Like, it's not this is not a bad idea. It's just more computationally expensive. I hope that answered the question, by the way. And yeah, like elbow method kind of stuff also comes to mind here, but that's what I also mean with like, pick a good metric. The elbow method itself is not necessarily a bad idea, but the hard bit is like, how do you have a metric that you can actually relate to reality? Like, that's the hard part. But anyway, okay. So far, so good, right? Like, I hope we kind of like it. But let's now have a look at the data set that I drew again. So you notice, maybe, right, that I drew a data set with two colors in it. So I've got something over here, and the rest is orange. And I'm drawing this with a trackpad instead of the pencil because it's broken somehow. But I hope that people sort of can appreciate that, yeah, like, technically we are dealing with two classes here. So maybe there's something we can do there as well. And one idea that you might have, or at least that's something I considered 5 years ago, is we could just train a Gaussian mixture system on the blue dots. Like, ignore all the orange bits. And then when we do that, we're able to do outlier detection, we're able to sample, and we get a likelihood score. But we can also do that for all of this orange stuff, right? Like, not the blue stuff. I can't draw on the trackpad. But like, we can also do that for all the orange points. And the same argument holds. We have a thing for that class that can do outlier detection. We have a thing for that class that can do sampling, but we also got the likelihood score. And that means we also have a classifier. Because what you can do is you can say, for the blue Gaussian mixture model stuff, I'm able to predict likelihood scores for whatever new data point comes in. I'm also able to do that for the orange variant. Both of these two groups can have different numbers of components, let's say, but I get a likelihood score. And you can just assign the class to whatever whatever color gives the highest likelihood score. That's something you can also totally do. So taking a step back, in my mind, like, the really cool thing at play here is we kind of have a model algorithm. Like, if you start from the perspective of let's do something with a probability distribution and let's use Gaussian mixture models for that, which are pretty good, then suddenly we're able to do outlier stuff, classification stuff, and sampling, and other likelihood stuff, so to say. Like, the fact that we have this building brick that's a probability distribution, good grief, that makes it really, really flexible. And then I'm not even talking about regression, which we'll get to in a bit. Because there's also some regression tricks you can do with this Gaussian mixture model as well. But, oh, someone is asking a question. Have you tried the Bayesian Gaussian Mixture Model? They are great for having low assumptions of the number of components. All right, so that's an answer to someone else's question, but that'll be fine. So, what I would like to do now is just give this kind of a quick demo of something that I've built, I think 5 years ago. So at some point, I had noticed all these observations, like, hey, you can do these really cool things with Gaussian mixture models, but maybe it would just be beneficial if the code for this was just slightly nicer. So I made a scikit-learn plugin. I'm just going to make sure that it's installed. So pip install scikit Lego. I think it's already installed. Oh, it's not. Okay, so we're going to install that real quick. But the thinking behind Scikit Lego is just that there are some Lego bricks and some components that are just kind of neat to have around. I'm just going to copy something from the docs that I had there. Oh. I'm I'm going to have to remove a couple of new lines that have appeared miraculously. That's a bummer. But that should be okay for the demo. So let's move some of that stuff up. Get that one in, get that one in. There we go. Okay. So what does this code do? I'm first just generating a data set, a random data set from scikit-learn, simulated data. All this stuff is sort of well understood, but what I'm... Annoying Docker update message. But what I've got here is something that I like to call a Gaussian mixture classifier. And under the hood, that Gaussian mixture classifier is just doing all the stuff that I described earlier. So it's going to run Gaussian mixtures on both separate classes. It's then going to figure out likelihood scores and all that good stuff. And here's what that could kind of look like. So let's just run this bit of code. So this is the data set in question. So I've got yellow dots and I've got purple ones. Both of them are going to get the Gaussian mixture model sort of training procedure. So I have a purple distribution, let's say, as well as a yellow one. And then if I were to say, well, maybe there's a new data point coming over here, well, how likely is that to the purple distribution? How likely is that to the yellow distribution? I could do that for a whole bunch of points. And then you can see that I've got this decision boundary down below for this particular data set. So you can see that if I were to use Gaussian mixtures as like the basis for classification, then I get a system that's very, very non-linear. Like it's able to do like the non-linear classification stuff pretty easily. So that's actually kind of nice. But of course, why stop there? So another thing you can also do is do that outlier detection trick that I mentioned. And I'm now going to copy that code from the docs. And I think the combination of these two things is the main point I wanted to drive at. So again, I can paste. Again, I'm going to have to remove these I don't know where they come from, these excess white spaces, but there we go, new block of code. So in this case, I'm doing practically the same thing. It's just that now I am fitting a Gaussian mixture model outlier detector instead of a Gaussian mixture model classifier. Both of these two things are things in Scikit Lego mixture. But the kind of the cool thing you can do with this is the trick I just showed you. You can say, well, there is a likelihood of points given 16 Gaussians on this entire data set, and then we can also, because we've got likelihoods, specify a region where we've probably got outliers, and we can also specify a region where we probably don't. If I recall correctly, yeah, there's some sort of threshold here. I'm going to set that threshold a bit lower now for demo purposes, but hopefully you kind of catch the idea. Like I'm able to make it thinner, I'm able to make it wider. Actually, in this case, I wanted it to be wider, so I'm going to go ahead and do that. But lo and behold, like we can turn the Gaussian mixture model into a new scikit-learn component just for classification, even though under the hood it's really just reusing the same stuff. So why is this so useful then? Like, why would I sort of drive home the fact that you really can do both of these two things at the same time? Well, that is because I think sometimes you should do both of these two things at the same time. So let's go back up. imagine that you're in this situation, right? Like we've got a data set that actually looks like this. It never does, but let's assume that it does. Then right now, we are in this awkward situation where if I get a new data point over here, right? Then I would see a data point where I've never seen a data point before. But it is a data point that is definitely closer to the purple distribution. So the underlying algorithm for classification is going to say, okay, my heuristic says that's a super high score for purple, super low score for yellow. So my probability value is going to be super high that you're purple. Even though that's in a region where we've barely ever seen any data before. So that actually kind of stinks. But what if we now come up with a system where we actually do a bit of outlier detection first? Well, in that case, that same data point that was sort of over here, that's in the region where we can declare it's an outlier. Okay, so that gives us an opportunity to say the classifier is not allowed to make a prediction because it's in the zone where we've never seen data before. So we can kind of do this thing where we raise a won't predict flag. And that's actually, as far as like AI safety goes, a pretty dang good idea that more people should actually consider. If you're building an automated system that's going to be making decisions, it is a really good idea to consider when an algorithm should not automatically make a decision. And even though the outlier detection mechanism is not going to be necessarily perfect, it is a safety feature that I really wish more machine learning pipelines would just plain consider. It really is a shame that this is a rant I sometimes give at talks and conferences and stuff. But I've been giving this rant for over 10 years now, and people still don't. I kind of get it because most machine learning textbooks don't talk about this stuff. But the thing that I think is just really, really cute about this Gaussian mixture is that it really can handle all of that technically. It's this one little Lego brick, this one little mother algorithm, you could almost say, that can really handle all those use cases that are usually like pretty deep concerns. And again, it's not perfect, but boy, is it a fun Lego brick to just build systems with. Okay, I need to calm down now because I was ranting a bit there. But I do hope that people agree and that they kind of look at this and kind of go like, oh yeah, these are definitely like neat properties. These are things that are definitely just kind of interesting. So if this does sound interesting and you want to play around, know that yeah, let's actually look at the docs for a bit there. Whoops, wrong window. So if you are interested in this, you can type scikit Lego. I am tooting my own horn a bit here because it is a package that I made, and definitely check out scikit-learn first because some of the tools in here are definitely on the experimental side. But if this does sound interesting, I did write this guide all those years ago that sort of explains this in a little bit more detail, and you can copy this code locally and also kind of play with it. It is also fun to see how sort of this behavior changes when you give it different data sets. That's also kind of fun. So you can also do the draw data thing and kind of see where it makes a mistake. One thing that is also good to know is that we have variants for the Gaussian mixture model like the Gaussian mixture model is the main Lego brick under the hood. But if you really wanted to, we also feature the Bayesian variants as well. So if you want to have a system where you're fine with throwing more compute at it, but you don't want to worry about those number of components, then you can also just call the Bayesian Gaussian Mixture Model classifier and the Bayesian Gaussian Mixture Model detector as well. Like those are also things you can just go ahead and pick. That is something I wanted to just briefly show. By the way, if people have fun ideas for algorithms, do check out Scikit Lego. That's kind of a nice little home for the more experimental but useful things out there. But this will be a great time to maybe ask some questions because I want to move on to like sort of almost wrap this stuff up, but maybe to show off a few blog posts that I wrote a couple of years ago that sort of go an extra mile with these mixtures. But I do want to give the opportunity for people to ask questions, maybe. No? Going once. Going twice. All right. So, one thing you could also do with these Gaussian mixture models is combine them with neural networks in fun ways. Oh wait, there's a question that's have you considered writing a textbook? Real world machine learning is good, but 8 years old. I will gladly take that as a compliment. I can confirm that I am actually already writing a book, so I'm not going to write another one. But I can't announce anything formally about that just yet. But I am writing a book. That's already sort of happening. I'm not gonna. It's not going to be a machine learning textbook though, because mainly because I think there's already a couple of really good ones out there. If I were to make any suggestion out of the blue, if you are like mathematically trained a little bit, like you know your calculus, probability theory, and linear algebra, then probably the Bishop book is one of the better ones. There are tons of other ones, and I would also argue go to PyData's as well. Some of the PyData videos like outshine a book any day. But the Bishop book is a pretty damn decent book. Like I am happy that I've got it on my shelf here at home. Um, that said, that is an unrelated question to Gaussian mixture models, so I'm going to pivot the conversation back to that. And I'm just going to go to my personal blog to grab like 2 old blog posts that I wrote. One is this one. It's about Gaussian auto-embeddings, and the other one is called feed-forward posteriors. I'm going to zoom in because I'm going to mainly talk about a few of the pictures, but I do think there's a couple of like clever ideas here. And yeah, let's talk about this one first. So let's say, right, that we're dealing with an autoencoder in neural network land. What does an autoencoder do? Well, an autoencoder is basically just stuff goes in, and the stuff that goes in is also the stuff that we try to predict that goes out. But we have this sort of layer in the middle over here that is very small and constrained. So you can imagine I've got like 100 inputs going in, but maybe in the middle I've only got 2 outputs, and then at the end I have like hundreds of them again. The thinking is that then that layer in the middle, that's kind of got to do compression in a way. Like it needs to figure out how to best represent similar things together, because it's only because the amount of information that it can store in 2 dimensions is just way smaller. So it needs to be doing something clever, doing something. You're kind of forcing it to cluster. Is kind of the hope usually with these sorts of systems. But that also means that in that low dimensional space, you hope that stuff kind of clusters together. So I made this drawing over here, and I was kind of looking at that, like, you know, it's not a bad drawing, but given that we've got this encoder thing and the decoder thing, what might we be able to do? And I kind of started thinking, well, it would be kind of nice if like that intermediate state, like those clusters that appear in the middle, what could we do if we train a Gaussian mixture model on that? Maybe we can do some fun stuff. That's like the thinking. And I kind of explained everything just now before, like hopefully it's not a big surprise, but if data comes in and you've got like your Gaussian mixture model on that latent state, I mean, you can make predictions, like you could use that just for classification. You can do outlier detection stuff. But in this particular case, the sampling is actually a little bit more interesting too. So the fact that we've got something going in that has to represent something that goes out as well, and the fact that we're able to sample in that low dimensional space with those Gaussians might also mean, I think that that's kind of interesting, that we can also generate data more easily. The following that I'm about to say is less of a mystery if you're well versed with neural network stuff. If neural networks are kind of you, what I'm about to say might sound a bit more crazy. But the experiment that I did in this blog post is I figured, you know, let's first train an encoder. So the line above is the stuff that's going in, and the line below is the stuff that's coming out of my algorithm. So we've got the autoencoder thing working. That's great. But then what happens if I were to sample from that latent state? And what I'm doing here is I'm saying, well, let's just sample a bunch of ones. Like this is the MNIST data set. Those are like handwritten digits. And I told my algorithm, let's sample from the Gaussian mixture that's around the cluster of all the zeros, and let's see what the decoder comes out with. And you can actually kind of see that we get a bunch of zeros out that all look a little bit different. And we can do the same thing with numbers, different numbers, etc. So that's kind of nice. We can sample handwritten digits. And similarly, there's also a data set called Fashion MNIST, which is the same thing as MNIST, the hand drawing thing, but for clothing. And you can also see that I'm able to like sample a bunch of shoes and a bunch of t-shirts and a bunch of pants. So that worked kind of all right. What I also wanted to do is like, what happens if I sample not from like a class-specific Gaussian, but what happens if I sample from like all the Gaussians sort of put together? And then you do see that I'm able to decode stuff, but it's just a little bit less pronounced. I do think the quality that you get from sampling a class-specific Gaussian is just a little bit better. But yeah, like this is actually also a pretty neat idea for generative algorithms. Like that's something like if you're just trying to hack something together, this does actually kind of work. So if you're dealing with a system where we've got an embedding and from that embedding we're generating something, if you've got training data, then you can train a Gaussian mixture on that embedding, and then that might be a thing you use to steer the algorithm into sampling something very specific. I'm definitely eager to do some experiments with that. And also just to emphasize like that there isn't evidence that there's like a manifold here. Like if I were to just sample randomly from this latent state, like not like ignore the Gaussian mixture, and if I were then to send that to the decoder, then pure gibberish comes out. So definitely something has been picked up by the Gaussian mixture. It's not just if you sample from this latent space that you always get something pretty out. No, it's actually the fact that the Gaussian mixture was able to pick up something of a pattern, and that is definitely helping when I'm trying to generate numbers using a neural network. And yeah, like another thing that I do think was kind of interesting, what you could also sort of do if you were to theoretically, right? If you were to grab the Gaussian from the 5, and if you were to grab the Gaussian from the 3, and you were sort of to say, well, can we sample on the path between those two? Then if you were to do that on the output layer, you would just sort of blend the two numbers. But if you were to do that on like the latent space, what you then get is kind of if you go from a 3 to an 8, you kind of get a 3 that starts to look like this in the beginning, and then slowly starts closing loops. So I also thought that was kind of an interesting thing to show. This is a bit of a detail in the larger scheme of things, but again, the fact that another thing you can also do, by the way, is you've got a Gaussian mixture on the zeros, right? That Gaussian mixture consists of, let's say, 7 normal distributions, and you could maybe argue that each normal distribution describes a slightly different style of zero, if that makes sense. So we've got like a mixture of distributions that represent all zeros, but that mixture of distributions consists of multiple Gaussians. You can also sample from each Gaussian, and when you do that, you also just kind of notice that they each encode a bit of style as well. That's a little bit distinct, which I thought was interesting. So as I was looking at ladies' shoes, for example, I was able to see that 2 of the Gaussians depict like heels. Thought that was kind of interesting. But anyway, like, I can share this blog post if people are interested. Let's actually do that. People might be. So I will just copy this blog post into the chat. But like, this is definitely like oh yeah, you can also do stuff outside of scikit-learn in neural network land with this. This took me a while to write, but this was definitely like a fun experiment, and it would have been way harder to do stuff like this if I didn't have that Gaussian mixture. Finally, like another thing that I do want to just mention here. Let's consider a regression problem that looks like this. I'm going to dive into the details of the rest of the charts, but I just want to, let's just look at these 2 data sets for now. So I'm going to make the screen bigger because I'm about to do like a regression argument. So let's pretend that these are 2 data sets that I'm interested in predicting, but I'm interested in doing regression. So I've got stuff on the x-axis, and what I would like to predict is stuff on the y-axis. Well, then these 2 data sets are typically insanely tricky for standard regression algorithms. And the reason is, if I were to be x is -5 over here, there's actually like a region of points where a prediction would make sense. Then there's a gap, and then there's another region of points where a prediction might make sense. So this is one of those times when a point estimate is not going to be that useful, because what you kind of want to predict is a probability distribution that has 2 hills, so to say. Turns out Gaussian mixtures can totally do that because they emit a distribution. You have to be a little bit clever about how you code that up, because you do have to sort of throw x and y into the Gaussian mixture mix, and then you're gonna have to do a good likelihoods trick to make sure that you're capturing it the right way. But you can hopefully intuitively imagine we're dealing with a probability distribution. If the output of the system needs to be a probability distribution, the Gaussian mixtures can also totally help out there. So people in neural network land have also tried to do this, by the way. So the way that they went about it is they said, well, let's just have a neural network going forward, but we're going to predict that one part of the neural network is all the average values of each Gaussian. then another part of the algorithm of the network is going to represent all the sigma values, like how wide should the distribution be. And then we've got this other part of the network where it has a sum to 1, and each weight is going to say, oh, for this data point going in, these are the Gaussians that matter most. Like, it's going to pick the Gaussian values, so to say. And there's different activation functions you got to do to write all this up, but you could argue this is a neural version of a Gaussian mixture model. That's also something people have been trying out. This architecture seemed pretty clever to me. I'm a little bit surprised to see that it's not really being used as much anymore, so I'm kind of curious if there's a reason why. But the point of this blog post was to show that if you are going to train neural networks that way, you do get a distribution going out. But one of the conclusions that I've also got was you can also just use the Gaussian mixture model from scikit-learn, and that's a whole lot faster in training a big neural network to do this sort of thing. So anyway, that's a bit of a diversion, a bit of an edge case. But I do think it's also like another nice example of just how flexible these Gaussian models can be. Like, you can use it to emit a distribution, and also in regression land, that can just be super useful. Okay, end of speech, because I've been talking and ranting for a bit, and I can't imagine people would appreciate a breather at this point, because I have been dunking a lot of like info maybe. But the short story of this is like, hey, another cool aspect of scikit-learn in this case is that it doesn't just do stuff that fits predicts and can do the machine learning thing for you. It is also that scikit-learn comes with very, very useful Lego bricks to build other systems with. And I think that this Gaussian mixture is like one of those really, really neat examples of something you might need in your day-to-day. Like, sometimes you want to just fit a probability distribution, and a Gaussian mixture is a pretty good system for that. One thing, is there a... Yeah, so there's, yeah, it's not the only thing that can do density estimation I do want to mention. There are also some other things you could do. And if I recall correctly, it was sort of in a bit of a weird place. Yeah, so if you go to the neighbors submodule of scikit-learn, then you have the kernel density method, which is a different, there's a user guide for it. It is different than Gaussian mixtures, because Gaussian mixtures have like a very strict way on how they work, and these systems are a little bit more more heuristic based. I think you could kind of say, but yeah, there's just all sorts of tricks to come to distributions. That's also the kind of the story here. Gaussian mixture models are a very sort of principled and mathematically somewhat elegant way of going about it, but there are also more heuristic approaches that you could also just have a look at. So these kernel density estimators also have the score sample method and the sample method, etc. Could you please introduce a couple of references papers for that neural network? Oh God, I think if you go to my blog post, there's links. So there's a really, really old book from Bishop that talks about it. But that book from Bishop that I mentioned, the same author wrote a paper in 1994 that discusses this. Yeah, you can kind of see from the font that it's a bit of an old paper. But yeah, if you are interested in like the full mathematical rigorous details, check this one out. The blog that I linked in the chat has this link, and I will try to make sure it's also added to the show notes. But yeah, if you're interested in the paper, here you go. One thing to maybe also remember is that the math is great, but the downside of the Gaussian mixture approach is that the data sometimes doesn't necessarily appreciate a Gaussian distribution. Like, if you're dealing with categories, let's say, yeah, maybe categories are better for with a Dirichlet distribution or something like that. But the downside of those distributions is that they typically have a very hard time fitting to a gradient update. Normal distributions have mathematically sound properties such that a gradient update can actually happen. Not every probability distribution, especially in categorical land, has that property as well. But yeah, if you look for Gaussian density, what's the name of it? Density mixture networks. That's the term you want to Google if you're interested in these systems. Again, on the benchmark that I've got on my blog, the Gaussian mixture thing just works way faster. So if you want to do the quick and dirty thing and not worry about neural networks, like just ignore all the other things. Just start with Gaussian mixtures. I think is a fine bit of advice as well. After doing this, I'm actually eager to do more stuff with Gaussian mixtures on embeddings. Actually, I think it's time to maybe do more cool stuff there for generative algorithms. I can definitely imagine it would you can do some good with that. But more on that later. I guess this is almost the time that people are going to go back to lunch, and if so, great. If there are any extra questions, I will be around. The one thing I do want to mention is I won't be doing a live stream next week. Believe it or not, after doing this for 2.5 months, I also need a vacation. So I will be doing something of a family trip. And next Friday, I won't be available to do the live stream. Definitely send me suggestions for other stuff that I might want to do, but I will not be doing the live stream. We are going to launch the next episode of the podcast. Might be my favorite conversation of the year. So definitely check out the podcast player. Sign up for that Sample Space podcast if you haven't already. So great interview coming next week, but I won't be doing the live stream. Do keep sending me good questions and things to do because I am interested in exploring things more. What I will be doing probably is, so next week I will be off. The week after, I think I will look into quantization techniques for embeddings because there might be a trick or two we can do in scikit-learn land with those. And I do think it'd be nice to explore that domain a bit more as well. Because there's embeddings can be used in scikit-learn, and the fact that we can sort of do lightweight quantization in that realm is pretty cool. But you might have to rethink how embeddings work because we have to talk about bin packing integers, which is also a fun topic. But yeah, okay. Hopefully this was interesting and fun. As always, thanks for tuning in. Reach out to me on socials if you have like specific questions, or if people are interested in like more resources. I'm definitely here for that. But yeah, having said that, thanks for listening. Have a good one. Enjoy the weekend.